Hello, everyone. My name is Michael Jacobson. I'm a PhD student in Dr. Myung-Gi Kim's Rehabilitation Robotics Lab. We are located within the UIC's Department of Mechanical and Industrial Engineering. The other PhD students that I collaborated with on this project are Pratikith Kantaraju, Hyung-Kung Jong, and also we collaborated with a Dr. Matthew Major from the Northwestern Feinberg School of Medicine. The presentation I will be detailing is the personalized ankle foot prosthesis stiffness and how it may improve user comfort of walking. So an estimated 500,000 individuals in the US have a below knee amputation. User comfort is also strongly associated with the residuum socket interface pressure. So because there are pressure intolerant zones of the residual limb within this custom socket, there can be discomfort during the dynamics of walking. And it's also been proven that interface pressure can be influenced by ankle foot prosthesis stiffness. So by inherently tuning this prosthesis stiffness, we can augment the interface pressures within this residuum socket. So for our pressure cost function development, we use this equation on the left-hand side, where the normalized peak pressure, denoted by the N subscript peak, is equal to the mean of the sum of lateral and anterior socket pressures, which is mu subscript L plus A, divided by the mean of the peak pressure values. Now on the right-hand side, you can see this is an image of a socket for a transtibial amputee. And you can see the color yellow is the lateral pressure sensor that would be fitted into the socket. And the green would be the anterior pressure sensor that would be fitted into the socket. And that is how we obtain our pressure measurements within the residuum socket. So the normalized peak pressure was sampled for 90 seconds to calculate the pressure cost for each stiffness parameter iteration during the human in the loop optimization. Now we'll detail this optimization next. So for the human in the loop optimization, this figure essentially overviews the whole loop that we call human in the loop. Subfigure A is the torque trajectory using the stiffness parameter. So you could see on this ankle angle torque graph that as we change the stiffness value, it changes the shape and peak torque of the curve. For subfigure B, the AFP emulator with a participant with below knee amputation, so walking with an interface pressure sensor. So you can see in this subfigure how we have an off-board actuation system, meaning there's an actuator off-board and our end effector is tethered in the sense where a tether connects to this actuation system. And also depicted is the socket interface pressure. So again, the pressure sensors are fitted within this residuum socket. C, again, is the residuum socket interface pressure cost function that I had previously detailed in the previous slide. And then D, so once we obtain this cost function, D is the Bayesian optimization, which selects the stiffness parameter based on the cost function. So you can see on the top figure is our Gaussian process curve where a minimum cost point is used to determine the next optimal parameter. And on the bottom figure is our acquisition function, which is choosing the next best parameter. So our experimental protocol, as you can see on the left-hand side, I have an image or a video rather of both participants walking with the ankle foot prostheses and the entire emulator system and the off-board actuators. And you can see detailed on the bottom of that is our block diagram, which is kind of a nice visual interpretation of our experimental protocol. So it is a 3-day protocol. Day 1 is the acclimation day, which is used to familiarize the participant with the just the device itself. And we also use this kind of as a day to where we can fit the device to the socket, because each individual has a custom socket, and we need to cut a pylon and then fit the device. And we have a prosthetist who comes in and helps with that. Day 2 is the human in the loop optimization training day. So it's a training day in the sense that we go through the entire optimization scheme, but we don't collect or analyze the data. It's just used for the subject to be trained. And then day 3 is the data collection. So we do the same exact optimization, but now we collect the data and we analyze. And the demographics of our two pilot study subjects were age 38 and 59, gender, male, female, weight 95 kilos and 60 kilos respectively. So for our human in the loop optimization results, you can see on this left-hand figure is the Gaussian process for subject 1 on the top and then subject 2 on the bottom. Is pressure cost on the y-axis, followed by stiffness on the x-axis. And you can see how varying optimal parameters were converged for each subject. And then also in our bar graphs, you can see how blue is the weight-based condition. So this condition was chosen just based on the subject's weight. So as I showed in the previous slide, each subject would have an inherent weight-based condition. And then the green is the optimal condition chosen by the optimization. So the personalized AFP stiffness reduced normalized peak pressure. It increased user comfort and reduced metabolic rate compared to the body mass weighted stiffness for both subjects. Perceived effort was also reduced for one subject. So in conclusion, personalized ankle-foot prosthesis stiffness has the potential to reduce residuum socket interface pressure and therefore increase comfort and reduce walking effort during walking for individuals with below knee amputation. Again, I want to thank everyone for your time. I value any sort of questions, comments, and concerns as well. Again, we are all from the UIC's Mechanical and Industrial Engineering Department and also the Northwestern Feinberg School of Medicine. This work was also funded by the U.S. Department of Veteran Affairs. And again, thank you all for your time.